Let's begin this chapter with a quick recap of what we have learned about triangles in previous classes. We have learned that two figures are said to be congruent if they have the same shape and the same size. All circles with the same radii are congruent. All squares with the same side lengths are congruent, and all equilateral triangles with the same side lengths are congruent. Two figures having the same shape and not necessarily the same size are called similar figures. In this chapter, we shall study about those figures which have the same shape but not necessarily the same size. In particular, we shall discuss the similarity of triangles and apply this knowledge in giving a simple proof of Pythagoras' theorem learnt earlier. Learning objectives. At the end of this chapter, you will be able to interpret similar figures, state the theorems relating to similarity of triangles, cite the criteria for similarity of triangles, determine the areas of similar triangles, prove Pythagoras' theorem using similarity of triangles. We can observe two circles do not have the same radius. They are not congruent to each other. Some are congruent and some are not, but all of them have the same shape. So they all are what we call similar. Two triangles, triangle ABC and triangle DEF, are similar. If one, angle A is equal to angle D, angle B is equal to angle E, angle C is equal to angle F, and 2, AB upon DE is equal to BC upon EF is equal to CA upon FD. Symbolically, we write the similarity of these two triangles as triangle ABC equal to triangle DEF, and read it as triangle ABC is similar to triangle DEF. The symbol stands for is similar to. A girl of height 90 centimeter is walking away from the base of a lamp post at a speed of 1.2 meter per second. If the lamp is 3.6 meter above the ground, find the length of a shadow after 4 seconds. Solution: let AB denote the lamp post and CD the girl after walking for 4 seconds away from the lamp post. You can see that DE is the shadow of the girl. Let DE be x meters. Now, BD is equal to 1.2 meter into 4 equal to 4.8 meters. Note that in triangle ABE and triangle CDE, angle B is equal to angle D. Each is of 90 degrees because lamp post as well as the girl are standing vertical to the ground. So, triangle ABE is equal to CDE, AA similarity criterion. Therefore, BE upon DE is equal to AB upon CD. That is, 4.8 plus x upon x is equal to 3.6 upon 0.9 into 90 centimeter equal to 90 upon 100 meter equal to 0.9 meters. That is 4.8 plus x equal to 4x. That is 3x is equal to 4.8. That is x is equal to 1.6. So the shadow of the girl after walking for 4 seconds is 1.6 meter long.
Properties of the ratios of areas of two triangles. Observe the following figure. Write the areas of each triangle. Then write the ratio of their areas. Students work in pairs and produce the following results. Area of triangle ABC is equal to half multiplied by base into height, which is equal to half multiplied by BC multiplied by AE. Area of triangle PQR is equal to half multiplied by base into height, which equals to half multiplied by QR into PT. Therefore, area of triangle ABC divided by area of triangle PQR, which equals to half multiplied by BC into AE, divided by half multiplied by QR into PT. this equals to BC multiplied by AE divided into QR multiplied by PT. Hence, the ratio of the areas of two triangles is equal to the ratio of the product of their bases and corresponding heights. If area of triangle 1 is A1 and area of triangle 2 is A2, then this property can be expressed symbolically as A1 divided by A2 is equal to B1 multiplied by H1 divided by B2 multiplied by H2, where B1 and B2 are the bases, H1 and H2 are the heights of the respective triangles. For triangles with common or equal base, in the adjoining figure, triangle XYW and triangle YZW have a common base WY. Therefore, area of triangle XYW divided by triangle YZW is equal to XY multiplied by WY divided by ZU into WY equals to XY divided by ZU. Hence, the ratio of the areas of two triangles with same base is equal to the ratio of their corresponding heights. A1 divided by A2 is equal to H1 divided by H2 if B1 is equal to B2. For triangles with same or common height, in the figure, triangle PQT and triangle PQS. Therefore, area of triangle PQT divided by area of triangle PQS is equal to TQ multiplied by PR divided by QS multiplied by PR is equal to TQ divided by QS. Hence, the ratio of the areas of two triangles with common or equal heights is equal to the ratio of their corresponding bases. A1 divided by A2 is equal to B1 divided by B2 if H1 is equal to H2. Note, the bases TQ and QS are collinear and triangle PQT is equal to triangle PQS have a common vertex P. Such triangles always have the same heights. For triangles with common or equal bases and equal heights, in the figure, segment MN is parallel to segment LK. You know that the triangles that lie between two parallel lines have equal heights. Let area of triangle MLK is equal to A1 and area of triangle NKL is equal to A2. Area of triangle MLK divided by area of triangle NKL is equal to LK divided by LK. LK is common base. A1 divided by A2 is equal to half. A1 is equal to A2. Hence, the triangles with common or equal bases and equal heights are equal in the areas.
A famous Greek mathematician, Thales, gave an important truth relating to two equiangular triangles, which is as follows. The ratio of any two corresponding sides in two equiangular triangles is always the same. It is believed that he had used a result called the basic proportionality theorem, now known as the Thales theorem, for the same. Click on Basic Proportionality Theorem to know more. Let's frame Basic Proportionality Theorem and prove it. Theorem states that if a line is drawn parallel to one side of a triangle to intersect the other two sides in distinct points, the other two sides are divided in the same ratio. Statement: a line parallel to one side of a triangle divides the other two sides into parts of equal proportion. Given in triangle ABC, a line drawn parallel to BC cuts AB and AC at P and Q respectively. To prove AP upon PB is equal to AQ upon QC, let the point P divide AB in the ratio of 1:m, where 1 and m are natural numbers. Divide AP into 1 and PB into M equal parts. Through each of these points on AB, draw lines parallel to BC to cut AC. Proof. Step 1. Cut AP into equal parts and draw lines through these points parallel to BC. Step 2. By intercept theorem, AQ is cut into equal parts. Step 3. By step 1, QC is cut into M equal parts. Step 4. By construction, AP upon PB is equal to 1 upon M. Step 5. By step 2 and 3, AQ upon QC is equal to 1 by M. Step 6. By step 4 and 5, AP upon PB is equal to AQ upon QC. Hence the proof. Now, let's check the converse of Theorem 1 and prove it. Theorem 6.2 states that if a line divides any two sides of a triangle in the same ratio, then the line is parallel to the third side. Theorem 2. If a line divides any two sides of a triangle in the same ratio, then the line is parallel to the third side. This theorem can be proved by taking a line DE such that AD upon DB is equal to AE upon EC, and assuming that DE is not parallel to BC. If DE is not parallel to BC, draw a line DE parallel to BC. So, AD upon DB is equal to AE dash upon E dash C. Therefore, AE upon EC is equal to AE dash upon E dash C. Adding 1 to both sides of above, you can see that E and E dash must coincide.
Applications of basic proportionality theorem. Let us learn the following properties that are based on the basic proportionality theorem. Number 1. Property of intercepts made by three parallel lines on a transversal. Number 2. Property of an angle by sector of a triangle. Property 1. The ratio of the intercepts made on the transversal by three parallel lines is equal to the ratio of the corresponding intercepts made on any other transversal by the same parallel lines. Given line L parallel to line M, parallel to line N. The transversal X and Y intersect these parallel lines at the points A, B, C and P, Q, R respectively. To prove AB divided by BC is equal to PQ divided by QR. Construction. Draw segment AR which intersects line M at point H. Proof. In ACR, segment BH is parallel to side CR. AB divided by BC is equal to PQ divided by QR. By basic proportionality theorem. Similarly, in triangle ARP, segment HQ is parallel to segment AP. RH divided by HA is equal to RQ divided by PQ. By basic proportionality theorem, AH divided by HR is equal to PQ divided by QR. By invertendo, AB divided by BC is equal to PQ divided by QR from 1 and 2. Hence, the property of intercepts made by three parallel lines on a transversal is proved. Property 2. In a triangle, the angle bisector divides the side opposite to the angle in the ratio of the remaining sides. Given. In triangle ABC, ray CE bisects ACB. To prove AE divided by EB is equal to CA divided by CB. Construction. Draw a line parallel to ray CE passing through the point B. Extend AC so that it intersects at D. Proof. CE is parallel to the line BD and AD is its transversal. Therefore, angle ACE is equal to angle CDB. Converse of corresponding angles test. Number 1. Now taking BC as transversal, angle ECB is equal to angle CBD. Converse of alternate angles test. 2. But angle ACE is equal to angle ECB given. Therefore, angle CBD is equal to angle CDB from 1 and 2 and 3. In triangle CBD, side CB is congruent to side CD, sides opposite to congruent angles. CB is equal to CD. Now, in triangle ABD, segment EC is parallel to side BD. Construction. AE divided by EB is equal to AC divided by CD. By basic proportionality theorem 5. AE divided by EB is equal to AC divided by CB from 4 and 5. 4. Hence, the angle bisector of a triangle divides the side opposite to the angle in the ratio of the remaining sides. Tests of similarity of triangles. SSS test. For a given 1-1 correspondence between the vertices of triangles. Two triangles are similar if the sides of a triangle are proportional to the corresponding sides of the other triangle. Illustration. In triangle ABC and triangle PQR, if AB divided by PQ is equal to BC divided by QR is equal to AC divided by PR, then triangle ABC similar to triangle PQR. Number 2. AAA test. For a given 1-1 correspondence between the vertices of triangles, the two triangles are similar if the angles of one triangle are congruent to the corresponding angles of the other triangle. Illustration. In triangle DFE and triangle XEY, we have angle D congruent to angle EXY, angle E congruent angle E and angle F congruent angle XEY, triangle DEF similar to triangle XEY. Number 3. SAS test. For a given 1-1 correspondence between the vertices of triangles, the two triangles are similar if two sides of a triangle are proportional to the two corresponding sides of the other triangle and the corresponding included angles are congruent. Illustration. In triangle XYZ and triangle RNS, if YX divided by RX is equal to XZ divided by SN and angle X is congruent to angle S, then triangle YXZ similar to triangle RSN. Number 4. AA test. For a given 1-1 correspondence between the vertices of triangle, if two triangles of a triangle are congruent to the two corresponding angles of the other triangle, the triangles are similar. You may verify that AA test is the same as AAA test. Converse of the tests of similarity. Number 1. Converse of SSS test. If two triangles are similar, then the corresponding sides are in proportion. That is, if triangle XYZ similar to triangle KLN, then XY divided by KL is equal to YZ divided by LN is equal to ZX divided by NK. Number 2. Converse of AAA test. If two triangles are similar, then the corresponding angles are congruent. That is, if triangle ABC similar to triangle PQR, then angle A congruent to angle P, angle B is congruent to angle Q, and angle C is congruent to angle R. If two triangles are similar, then the corresponding sides are proportional and the corresponding angles are congruent. Observe the pairs of triangles given below. State the rest and correspondence of similarity. In triangle ABC and triangle QRP, angle B is congruent to angle R, angle C is congruent to angle P. In correspondence, ABC is 1-to-1 correspondent to QRP. Triangle ABC is similar to triangle QRP. AA test of similarity. AN divided by LK is equal to 2.6 divided by 1.3 is equal to 2. Number 1. MN divided by SK is equal to 5.6 divided by 2.8 is equal to 2. Number 2. Now, in triangle AMN and triangle LSK, AN divided by LK is equal to MN divided by SK from 1 and 2. Angle MNA is congruent to angle SKL. Each is 90 degree. In correspondence, AMN is 1-to-1 correspondent to LSK. Triangle MNA similar to triangle SKL. SAS test of similarity. DE divided by PQ is equal to 3.6 divided by 5.4 is equal to 36 divided by 54 is equal to 2 divided by 3. DF divided by PR is equal to 2.4 divided by 3.6 is equal to 24 divided by 26 is equal to 2 divided by 3. EF divided by QR, 3 divided by 4.5 is equal to 30 divided by 45 is equal to 2 divided by 3. In triangle DEF and triangle PQR, DE divided by PQ is equal to DF divided by PR is equal to EF divided by QR. In correspondence, DEF is 1-to-1 correspondent to PQR. Triangle DEF similar to triangle PQR. SSS test of similarity. Properties of similar triangles. Reflexivity. Triangle ABC similar to triangle ABC. It means a triangle is similar to itself. Symmetry. If triangle ABC similar to triangle DEF, then triangle DEF similar to triangle ABC. Transitivity. If triangle ABC is similar to triangle DEF and triangle DEF similar to triangle PQR, then triangle PQR similar to triangle ABC.
The ratio of the areas of two similar triangles is equal to the square of the ratio of their corresponding sides. We are given two triangles ABC and PQR such that triangle ABC is similar to triangle PQR. We need to prove that area of ABC upon area of PQR is equal to AB upon PQ whole square equal to BC upon QR whole square equal to CA upon RP whole square. Now, finding the areas of the two triangles, we draw altitudes AM and PN of the triangles. Now, area of ABC is equal to 1 upon 2 BC into AM, and area of PQR is equal to 1 upon 2 QR into PN. So, area of ABC upon area of PQR is equal to 1 upon 2 BC into AM upon 1 upon 2 QR into PN equal to BC into AM upon QR into PN. Now, in triangle ABN and triangle PQN, angle B is equal to angle Q as triangle ABC is similar to triangle PQR, and angle M is equal to angle N, each is of 90 degrees. So, triangle ABM is similar to triangle PQN, AA similarity criterion. Therefore, AM upon PN is equal to AB upon PQ. Also, triangle ABC is similar to triangle PQR given. So, AB upon PQ is equal to BC upon QR is equal to CA upon RP. Therefore, area of ABC upon area of PQR is equal to AB upon PQ into AM upon PN from 1 and 3 equal to AB upon PQ into AB upon PQ equal to AB upon PQ whole square. Now, using 3, we get area of ABC upon area of PQR equal to AB upon PQ whole square, BC upon QR whole square, CA upon RP whole square.
Pythagoras theorem. Theorem 4. In a right-angled triangle, the square of hypotenuse is equal to the sum of the squares of the remaining two sides. Given, in triangle ABC, angle ABC is equal to 90 degrees. To prove, AC square is equal to AB square plus BC square. Constructions. Draw segment BD perpendicular to hypotenuse AC and ADC. Proof. In triangle ABC, segment BD is perpendicular to hypotenuse AC. Constructions. Triangle ABC is similar to triangle ABD. Similarity in right-angled triangles. AB divided by AD is equal to AC divided by AB. Corresponding sides of similar triangles. AC square is equal to AC multiplied by AD. 1. Similarly, triangle ABC is similar to triangle BDC. BC divided by DC is equal to AC divided by BC. Corresponding sides of similar triangles. BC square is equal to AC multiplied by DC. 2. AB square plus BC square is equal to AC multiplied by AD plus AC multiplied by DC. By adding 1 and 2 is equal to AC. AD plus DC is equal to AC multiplied by AC. ADC is equal to AC square. AB square plus BC square is equal to AC square. Converse a Pythagoras theorem. Theorem 5. In a triangle, if the square of one side is equal to the sum of squares of the remaining two sides, then the angle opposite to the first side is a right angle, and the triangle is right-angled triangle. If in triangle ABC, AC square is equal to AB square plus BC square, then angle B is equal to 90 degrees. Triangle ABC is a right-angled triangle. Theorem on 30 degree, 60 degree, 90 degree triangle. Theorem 6. If the angle of a triangle are 30 degrees, 60 degrees and 90 degrees, then the side opposite to 30 degrees is half the hypotenuse, and the side of opposite to 60 degrees is times the hypotenuse. Given, in triangle CAB, angle A is equal to 90 degrees, angle B is equal to 60 degrees and angle C is equal to 30 degrees. To prove, number 1, AB is equal to 1 divided by 2 BC. Number 2, AB is equal to BC. Constructions. Take a point D on ray BA such that AB is equal to AD. Joint points C and D. Proof. In triangle CBD, AB is equal to AD. Constructions. The point A is a midpoint of segment DB. 1. Angle CAB is equal to 90 degrees. Given, segment AC is perpendicular bisector of segment BD. 2. Segment AC is perpendicular bisector of segment BD from 1 and 2. Point C is equidistant from point B and D. Theorem of perpendicular bisector. BC is equal to DC. In triangle DCB, angle BDC is equal to angle DBC. Angles opposite to congruent sides. But angle DBC is equal to 60 degrees. Given, angle BDC is equal to 60 degrees. Angle DCB is equal to 60 degrees. Remaining angle of triangle DCB. Triangle DCB is an equilateral triangle. Each angle 60 degree is proved above. DC is equal to BC is equal to DB. Number 3. But AB is equal to 1 divided by 2 DB. Number 4. Constructions. AB is equal to 1 divided by 2 BC. Number 5. From 3 and 4. In right-angle triangle CAB, AC square is equal to AB square is equal to BC square. Pythagoras theorem. AC square plus 1 divided by 2 BC square is equal to BC square.
AC square plus 1 by 4 BC square is equal to BC square. AC square is equal to BC raised to the power 2 minus 1 by 4 BC square. AC square is equal to 3 by 4 BC square. AC square is equal to whole root 3 by 2 BC. Square root 3 by 2 BC. AB is equal to 1 by 2 BC and AC is equal to square root 3 2 BC.
Converse the theorem of 30 degrees, 60 degrees and 90 degrees triangle. Theorem 7. In a right-angled triangle, if the length of one side is times the hypotenuse, then the measure of the angle opposite to that side is 60 degrees. If in triangle ABC, angle BC is equal to 90 degrees and BC is equal to XAC, then angle A is equal to 60 degrees. Apollonius theorem is a theorem relating the length of a median of a triangle to the lengths of its sides. Given in triangle ABC, segment AD is median. To prove, AB square plus AC square is equal to 2AD square is equal to 2BD square. Construction. Draw segment AE, angle side BC, BED. Proof. In triangle ABD, angle ADB is smaller than 90 degrees. AB square is equal to AD square plus BD square minus 2BD DE. Application of Pythagoras theorem. Now in angle ADC, ADC is greater than 90 degrees. AC square is equal to AD square plus DC square plus 2DC multiplied by DE. AC square is equal to AD square plus BD square plus 2BD multiplied by DE. Number 1. Substituting BD for DC as BD is equal to DC. AB square plus AC square is equal to 2AD square plus 2BD square by adding 1 and 2.